Hi all. We now look at integrals that require you to first complete the square before you can perform any substitution and further on integrate. Let's look at C and D. The first one we'll look at is going to be C. And in C, when you look at that denominator, the first thing you want to do first is check if you can use any of the straightforward standard integrals, like for example, use substitution, or maybe just straight away integrate the way it is. And once those simple or basic methods fail, that is when you look at some other techniques. Here, for example, in the presence of that square root, you want to complete the square first to see if you can express it as either a minus x squared, or maybe as x squared minus a squared, like this. You know, if you have it in this form, which then matches either a or b there, you can then integrate it using a sign substitution or maybe a sec substitution. So let's try to complete the square and see what we end up with. So here, if we try to complete the square for the first one, so here we're looking at the integral dx of root of 3 minus 2x minus x squared. So we first focus on that denominator, rewrite it so that we just have x squared minus 2x plus 3, standard form of a quadratic expression. Then completing the square, I want the coefficient of x squared to just be positive 1, so I'll factor out negative 1 there. What remains here will be x squared. It will affect everything else, or multiply everything else by negative 1, implying that this will be positive 2x, and this will be minus 3. Then here I get half of the coefficient of the x term. So half of 2 will be 1, positive 1. So I'll add that. Of course, I have to square it. That's just 1 still. After that, I'll subtract it. Then that minus 3 is still there. Then next up, I'll remove the brackets. Remember the sign here was positive. So now I have minus 1. Get the x from here, the positive 1 from there. Together, square them. And then you still have the minus 1 here, minus 3 here. So here, you know, to say this whole thing can be simplified to just that. If you expanded this, you know, it will go back to just x squared and even account for that 2x we omitted. So now you have minus 1. This is x plus 1 squared minus 1 squared is 2, 1. Then combine with the minus 3, giving us minus 4. So this is what we end up having. So when we distribute that negative 1, we now have 4 being the positive 1 and the x plus 1 squared being the negative 1. So that now our integral has reduced to the integral of 1 over the root of 4 minus x plus 1 squared dx. So this is what we are now having. So this one can actually be integrated using the methods that we have seen already. And the only difference is that take this as one whole variable. So when defining our new variable, let's say u, we'll say since the squared term is the one which is negative, so we'll use sign substitution. So here we'll let u, not necessarily u, it's x we're letting, but here it's not x, it's all of this. So here we'll let x plus 1 be equal to a sine. Our a here is root of 4, which is 2 sine theta. Here when we get dx dy, dx d theta, we'll have this. The derivative of 1 there will be 0. So we'll have 2 cos theta. So that dx is equals to still 2 cos theta d theta. When we substitute in our expression, we now have this. This is now a root of 4 minus, where we have x plus 1, we'll put 2 sine theta, but this has to be squared. And then where we have dx, we'll put 2 cos theta d theta. So that now you have 1 over, this will be root of 4 minus 4 sine squared theta, and then you still have the 2 cos theta d theta. We see that it has reduced to something that we are familiar with based on the previous example. So 2 cos theta over, factor out 4, then square rooted giving you a 2. Then here you have 1 minus sine squared theta. 1 minus sine squared theta, we know that is cos squared theta, following that identity we've been using all along. The 2 and the 2 cancel, so you now have cos theta over root of cos squared theta. Root of cos squared theta will just be cos theta, so that this in the end will end up cancelling with that, leaving us with only d theta, the integral of that, which reduces to just theta plus c. Now, what is theta? To get what theta is, we recall that we said x plus 1 was equals to 2 sine theta. I think we defined that here. X plus 1 is 2 sine theta. So from there, we can now try to get what theta is. Divide both sides by 2, so you have sine theta is equals to x plus 1 over 2. And finally, theta is equals to sine inverse of x plus 1 over 2. So this is what theta is. So that our integral, the integral of dx over that was 4 minus, and that was 2x minus x squared. I think this is what we had. Where is it? It was this. It was 3. Oh yeah, that was minus x squared. Yes, 3 minus 2x minus x squared. 3 minus 2x, not 4. So this integral has reduced to, it was theta plus c, but we've just seen that theta is sine inverse of x plus 1 over 2, then plus c. So this becomes our solution. So let's see d. For d, we have x dx over x squared plus 4x plus 5. So in the same way, want to see first, is it possible for us to solve this using basic algebraic substitution? The way it looks like, if we let u be equals to that denominator and then differentiate u, it might not work, because when we differentiate, we'll have 2x plus 4. And this has nothing to do with that numerator, so it won't work, because we want, when you differentiate, you get something related to that numerator, which is just an x. So here, straight away, algebraic will not work. So let's try to complete the square for that denominator. Another thing that you might want to try here is using partial fractions. That might also work, but it might be tricky. So, but partial fractions here is another, not that it might be tricky. It might actually work. So if you can factorize this, let's try. You have 5x squared. So factors, you have the fact that this has to be positive. 5 and 1 would have been the best factors, 5 and 1. But for you to add these together, for one of them has to be negative, meaning the product has to be negative. So here we see that factorizing this will not actually work. So partial fractions here seems like it might be tricky to deploy. So let's try completing the square. So we'll get the denominator first. We'll focus on that denominator, which is x squared plus 4x plus 5. So here, the coefficient of the x squared term is already 1, so we are good there. So we'll go to the coefficient of the x term. The coefficient of the x term is 4. Half of it is 2, positive 2. So we'll add that positive 2, squared of course, then we'll subtract it. Then we still have that 5 at the end. Here, I always specify the sign to be positive because it's tricky when this is actually negative here. That negative is important because it's the sign that comes here. So if it was -2, the negative would have come between. But since it is +2, I'll get that positive and bring it here. the 4 here dies, knowing that when you expand this x squared, x plus 2 squared, it will still account for that 4 we have just omitted there. So of course the rest of it is still minus 2 here squared plus 5. So this is now x plus 2 squared minus 4 plus 5. So that we now have x plus 2 squared plus 1. So this is what our expression has reduced to, so that we have x dx over 1 plus x plus 2 squared. So in this case where you're dealing with both the squared term or the variable squared term and the constant term being positive, in this case the best you can use is a tan substitution. The square root of 1 is 1. So here we'll let this, the variable part, the whole thing. So here it won't just be x. We'll let that whole lot be the thing we substitute. So let x plus 2 being equal to a tan theta. Our a is 1, so we'll have 1 tan theta. We know this one is coming from the integral of, let's say, a squared plus x squared. So this is usually how it looks like. But instead of x here, we are using that whole lot, that x plus 2. So if you're not comfortable with letting x plus 2 being redefined, you can put an in-between step where maybe you say let y be equals to x plus 2. So that now you view it as the integral of 1 over 1 plus y squared. So but just get what dy will be, but dy will be equals to dx. So here this will be dy. So that now this is similar to that, which you can integrate using the tan substitution again. But if you can keep up, you can still just let the x plus 2 being equals to 1 tan theta, which is basically just tan theta. Knowing that when you differentiate with respect to x, with respect to theta, I mean, the left-hand side will just be dx d theta. The right-hand side, the derivative of tan theta is sec squared theta. So that dx is equals to sec squared theta d theta. When we now substitute, so since x plus 2 is equals to tan theta, it follows that x will be tan theta minus 2. So the 2 crosses so that we get the definition of what x is. So where there's x, we'll put tan theta minus 2. In the denominator, we have 1 plus. So where we have x plus 2, we see that is what we said is our tan theta. But that is squared, so we'll have that squared here. Then we have dx. dx is sec squared theta d theta. So now simplify this. The numerator will remain the same for now. The denominator, this becomes 1 plus tan squared theta. But we know that 1 plus tan squared theta is equals to sec squared theta. In other words, this and this are the same. So they get to cancel out, leaving us with the integral of tan theta minus 2 d theta. So this is now the integral of tan theta d theta minus 2 the integral of d theta. So when we integrate now, the integral of tan x will be negative ln of cos theta. Then the integral of d theta will just be theta plus c. So now that we're done integrating, we need to figure out or relate that theta to the original variable. So where did we define it? So we defined it here, where we had x plus 2 is equals to tan theta. So we said x plus 2 is equals to tan theta. So from here, we want to know what theta is. We also want to know what cos theta is. So firstly, directly from here, we see that theta will be equals to tan inverse of x plus 2. So this is what theta is. Now, how about cos theta? To know what cos theta is, we first have to recall that tan is equals to opposite over adjacent. But here we're seeing that tan is equals to x plus 2 over 1, since there's nothing here and there's nothing here. Usually, whatever the coefficient here is, that is what comes in the denominator here. But since it's a 1, this will be over 1. So if we view a right-angled triangle here, with this being our theta, and we're getting tan theta, opposite will be x plus 2. Hypotenuse, we do not know, but adjacent will be 1, since opposite over adjacent. From here, using Pythagoras theorem, we see that the hypotenuse will be x plus 2 squared plus 1 squared. And then, of course, this has to be square rooted. So in case maybe I present it a little bit differently, if the hypotenuse is taken as r, we know to say r squared will be equals to 1 squared plus x plus 2 squared, meaning that r will be root of 1 plus x plus 2 squared. So this becomes our hypotenuse. And since we now know what our hypotenuse would be, it follows that cos theta, which is adjacent over hypotenuse, will be 1 over the hypotenuse will be root of 1 plus x plus 2 squared. So this becomes our cos theta. And since we now have our cos theta and our theta, we can perform our substitution. So this becomes negative ln cos theta. Where we have cos theta, we're going to put 1 over root of 1 plus cos, not cos, that's open bracket, x plus 2 squared. So of course, like that. This is just cos theta. Then minus 2 theta. Theta, we saw that theta is tan inverse of x plus 2. So you have tan inverse of x plus 2. Then plus c. So this becomes our overall solution. Okay, so I hope you found this helpful. If you did, let me know in the comment section to join our daily math classes. So I do math, CEE, and Triple E. To join those classes, you can reach me on 260979 382081. So reach me through WhatsApp, and yeah, we'll let you know how to join the classes. So the classes are every day, and then we meet in the evening. All classes are online. Now guys, see you in the next video.